Thank you very much, Cristian. Thank you, all of you. It's great to see friendly faces. Actually, if you don't hide your face, I prefer to look at faces. Of course, if you feel like it's easier. Thank you very much for appearing. It's much easier. Hello, everybody. It's much easier to talk to see some faces in the next to the slide for me. All right. So here are my my slide. Share. I just, if it doesn't work, let me know. I think it works. How to be realist without wave function realism. I'm mostly talking about the relational interpretation of quantum mechanics, and I want to say a few things about it. Let me start by a general comment, which I think is nothing new. It's something you probably have heard, but for me, it's useful to keep in mind in general in these discussions, and remind you of a very well-known observation, wonderful observation by Richard Feynman, who says one of the amazing characteristics of nature, and the way he put it, it's very good, I think. We're surprised by this fact, but it's a fact about nature. It's a variety of interpretation schemes that it admits. So the same phenomena can be described in different manners, even at very large scale. I mean, classical mechanics admits a remarkably different ways of thinking about it, and so on and so forth. So we seem to, nature is remarkable to the fact that it seems to be possible to capture it with different conceptual schemes. All right, so what is Richard Feynman prescription about that? I mean, so what? Are we lost or what? Well, Richard Feynman advice is also super well known about that. It says every theoretical physicist who is any good, it's remarkable, he certainly was one of those, knows 6 or 7 different theoretical representations for the same physics. And here it seems to be saying, come on, they're all the same. Don't try to. Psychologically, we must keep them, we keep all the theories in our head. One of them will turn out to be more useful than others. So there's something subtle here. On the one hand, we have no real strong reason to prefer one. We might have some indirect reason to prefer one, but we don't know, also because we don't know which one might become useful later on. I think, to me, this is a very general, very useful attitude with respect to interpretations of quantum mechanics. I have, in recent years, spent sometimes somehow convincing myself that some interpretation don't work, or they have something not good, studying them, even writing little things, and then getting convinced that they're all coherent, they all work very well, in fact. So the discovery that nature has quantum properties, it's also the discovery that nature can be understood in different manners, as far as we know now. And of course, as Anthony just reminded us in the last talk, it might be that in the next step, understanding quantum gravity, one works better because it suggests something new. Or it might be that it works worse because what it suggests is not true. This is the way I view the situations. So I think it's good. We learn from each one of the currently most discussed interpretations, and we are strongly drawn to one or the other by what I would call metaphysical prejudices, which are very good. We should have metaphysical prejudices, but that's what they are, and a vague intuition about what could be most useful to go ahead. So from this perspective, this is a list of certainly not all good interpretations, but perhaps not even the one I prefer, but some which are much discussed today, sort of Copenhagen, whatever it means, with a microscopic world, cubism, relational quantum mechanics, which I'm going to take, pilot wave, of which Anthony gave just a version just now, the various physical collapse. This is, of course, physically distinguishable, and so is pilot way in Anthony version, and many world. Each one has some sort of metaphysical advantage for some reason that has a consequence that somebody loves it, and we have strong lovers of interpretation of quantum mechanics in our field, and each one has a cost. Each one asks us to make a big conceptual jump, or accepting something that our intuition says that it should be wrong, or that is too strong. And the preferences are often for one or the other, or preference, sort of philosophical preferences. So in this perspective, within this perspective, I'm going to tell you what relational quantum mechanics, which is an interpretation which I've worked for since the 90s, offer us a general lesson, and what is the sort of the metaphysical advantage of it, if you share some of the prejudices that are behind it, and also what is the cost of it, because once again, the cost of it is precisely what the cost of each of this interpretation, precisely what prevents some of us to adopt it as a natural way. The point is that quantum mechanics has no costless way of looking at it. So, so what do we do with relational quantum mechanics? One way of doing it is the following. This slide I've borrowed from a popular writer, Jim Boggart, is a journalist, who has presented the problem of quantum mechanics in one way, one of the many possible ways of viewing it. I'm not saying that this is the problem of quantum mechanics, as a difficult alternative between an anti-realist and a realist attitude. Each one of these, which he says, these are his words, is unsatisfactory for one reason or the other. And the way he presented is that there are some ways of thinking about quantum mechanics which are more in sympathy, in the wake of Bohr. Quantum theory is not about nature, but about what we can say about nature. And there is an opposite group, which is more realist in the way sort of Einstein, at least in one of the chapters of the great debate with Bohr, complained about Bohr anti-realism. And both these groups are disliked by some people for opposite reasons, because in the anti-realists, whether it's cubism or pragmatism, I mean, sort of Richard Healey way of looking at the theory, and even Copenhagen, if you try to view it also as a description of part of the universe, you don't say what is going on. You only say, you sort of assume, you talk about what you see about measuring apparata, about what you can do with the theory, what the theory can predict for you, and so on and so forth. So there's a strong instrumentalist attitude, which one could argue, if we had it, we wouldn't have taken seriously debate like Copernicus versus Ptolemy, or atomism versus non-atoms, which were, on the other hand, fundamental in the advance of physics. So it's a renounce of saying something more about nature. The other hand, the other side, we have a realist interpretation, like pilot wave, like many world, where you have nothing of that. I mean, they don't require an observer, they don't require a subject, they don't require talk about knowledge, anything like that. The theory is just cleanly defined in a way that Einstein would be happy. That's the world, and we describe it. But they all, and that's what the complaint there, they all add something to the theory, which, at least for the moment, unless Anthony's right, we don't see, right? Other copies of ourselves, hidden variables, whether it's the hidden variables of pilot wave or others, and so forth in the theory. So can we weigh both? Can we avoid both of that? Of course, I'm going to say that the answer is yes, we can avoid both at a cost, which is neither the anti-realist cost nor the excessive baggage cost that these two camps sort of blame one another. But there is a way of having both by being a realist in the sense of Einstein, but at the same time not being realist about the wave function. And this is exactly what the relational interpretation is. So it's an interpretation where there's no extra baggage, there's no hidden variables, there's no other worlds, there are no copies of myself, there's no phenomenon that I haven't seen yet, like physical collapse. There's nothing of the sort. There's only what the current tell us there is. Taking the theory as the best description of nature so far. And at the same time, there is no subject, there is no knowledge, there is no preferred point of view or anything like that. So I want to describe how relational quantum mechanics does that and argue that this is possible. And of course, say what is by gaining on staying away from the Scylla and the Charybdis of instrumentalists on the one hand, and to use the word of Bagard, a whirlpool of wild, unconstrained and metaphysical nonsense about nature of reality, which I don't share, but this is his world. One can avoid both. So how to do that? And the answer, I claim, can be obtained by just two considerations. Which I want to present to you. One is just go back to beginnings, namely remember how quantum mechanics was formulated first. And these are the people who created quantum mechanics. And the more I go back reading the paper of the 20s, the more I realize that it's Max Born, actually, who has created what we call today quantum mechanics. Together with Jordan, of course, and Heisenberg, and prompted by Heisenberg, and in a extraordinary turn of events, in parallel with what Paul Dirac, inspired by the same preprint by Heisenberg, did independently in England. And I put Pauli there because not because he's one of the creators of the theory, because he's the first one who actually used the theory to compute the spectrum of the hydrogen atom, which means understand the periodic table, before Schrödinger, of course. So 25. And this is in fact, this is the first Born-Jordan paper, where it's even before the paper with the third paper, the one with, the Zur quantum mechanic 2, the one with Heisenberg, in this paper, there is already quantum mechanics. So if you read this paper, you have all the theory, everything you need to compute everything. I mean, the rest is detail, really. The paper amply give credit to Heisenberg breakthrough, of course, 2 months earlier, in which has the first calculation with these funny non-commuting things. And the idea of the paper is very simple. You have variables. Instead of being numbers, they're a table of numbers, which are, of course, these are the jumps in the electrons. So the rows represent the orbit, the Bohr orbit to start from, and the columns, the Bohr orbit to arrive. So these are transitions, each entry. And the rule of the theory is super simple. The equations are the same as classical mechanics. So this, of course, is not a theory of something, is a general structure for a theory, like classical mechanics. So whatever object you have, which is described by classical mechanics in some way, its quantum property are described by the same variables, with the same equations, plus one. Only one equation, which it's for system in one dimension, is PQ minus QP is IH bar over times identity, which is an extra equation because, of course, these things don't commute. And in the same paper, to my surprise, because in all the histories of quantum mechanics, I've read something else, there is already very clearly expressed the idea that these matrix elements are probabilities, or determine the probabilities of the transitions. So Born got the Nobel Prize for probabilities, but usually one quotes the thing he published later on about the modulus square of psi. He had completely clear idea that this is a calculus about probabilities of jumps, of transitions, already in 25. So the entire theory is there, and quantum mechanics, in the way it was first created, is the following thing. There is a mathematics, which is the same equation of classical mechanics plus 1, xp minus px is I h bar. Dirac has the same structure, of course. It doesn't talk about matrices, it talks about just non-commuting variables, which is the same. These are values realized in observations, and I'll come back in a moment, and that's a point. And the prediction of the theory is which values can take the variables, which is a spectrum of A, which is just defined by this algebraic relations here. You can compute it. And given some observation, you can compute probabilities of our observations by suitable probabilistic calculus, by interpreting model square of matrix elements as probabilities in the proper way. Of course, if you start here, the confusing thing is observations. And the question is, how does nature know if anybody is observing? When is it that these probabilities of what? Of something being observed by whom? That's the obvious question from this perspective. And here is where relational quantum mechanics come in its, and that's a second main point I want to make. So first point, go back to the original formulation of quantum mechanics. Second point is the following. And that's a key point. I mean, that's a key slide of the story. This is Niels Bohr, of course, and Niels Bohr, in his long rumination about quantum mechanics, got to the idea that the key discovery with quantum physics is contextuality, meaning this is the first paragraph is from his writing, meaning that you have to keep the apparatus in the story. What are you measuring? And the way he put it is that in classical physics, the interaction between an object and a measuring apparatus can be overlooked, but in quantum physics, this interaction is an inseparable part of the phenomenon itself. So an ambiguous description of a quantum phenomenon is required in principle to include the description of the relevant aspect of the experimental arrangement. Now, this, I think, is the key discovery of quantum mechanics, and I'll argue in a moment to justify the mathematics exactly, but is misleading at the same time. Because when Bohr was writing this, the majority of the applications of quantum mechanics were, of course, in a laboratory. So you have a bunch of atoms emitting light, you have apparatus around them, you're talking about not the atoms by themselves, but the interaction between the atoms and the apparatus. But 100 years later, of total success of quantum theory, we're convinced that quantum theory is not about what happened in our laboratories, what happened in the sun, in the galaxy, structure formation in the universe, so on and so forth. So if we want to be mildly realist and not instrumentalist, we have to express the same idea, forgetting about apparata and forgetting about experimental arrangement, and just talking about what? Well, about a quantum phenomenon and everything which is around it, physically and concretely, with whom the system, the quantum system, is interacting. So the same contextuality can be re-expressed by slightly rewriting Bohr's account of contextuality in the following way. While in classical physics, the properties of an object are determined irrespectively from the interaction between this object and the others, quantum physics is a discovery that interactions are inseparable aspect of the properties. And that's a key point. Properties don't refer to an object alone. Properties refers to interactions. Properties talk about interaction. So the ambiguous description of an object requires the inclusion of the objects, the other objects involved in the interaction in which the first object manifests itself. So the idea here is stop talking about observation and talk about interactions in general. Stop talking about observables, where the word suggests that there is some observer, somebody with eyes, with machines, with apparata, and just talk about properties which are realized relationally between any two physical objects, whatever, without any need to be macroscopic or complex or whatever, when they interact. And the claim of relational quantum mechanics is this is possible. So quantum mechanics have been entirely reformulated in forgetting about any observer, forgetting about any specific aspect of macroscopic object or many degrees of freedom of objects. Of course, these have their own good features like the coherence and so on, but that's not required for the basic formulation of quantum mechanics. System, if you accept this these premises, the system by itself do not have properties, and that's a cost. Okay, so a property is not something that pertains to the system itself. A property is something that describes how the system affects something else. So property refers to interactions. And these are the key point, the two last line here. First, a property only makes sense at interaction time. When there's no interaction, it doesn't make sense to talk about properties. And second, if a property it shows up somehow in interaction with a system, then it's relative to the system and not necessarily to other systems. Relative quantities are very common in physics, right? The velocity of an object is relative to something else. The velocity of the moon relative to the Earth is something else than the velocity of the moon relative to the sun. The moon by itself doesn't have a velocity. So the idea of relational quantum mechanics is take any property of any object similarly to be relational, and don't necessarily pretend to properties when there's no interaction involved. So the quantum mechanics of the founding fathers here can be re-expressed without any reference to observers, to measuring apparata, by saying that the mathematics is what I said, values are realized in interaction with another system. So system S1 interact with the system S2, and then it manifests properties at this interaction. The values are given by the spectra. The probability of the properties with respect to S2, okay, are related by transition amplitudes, and the values are relative to S2. Namely, values of S relative to S2 do not determine the value of S relative to S3, and that's the key point. All right. Now, I claim, and I will then add a couple of slides, make it a little bit more precise, exactly what implies mathematically. I claim that this is a way of thinking about quantum mechanics sufficiently realist. I mean, realism is a vague word. So there's no involvement of subjectivity. There's no involvement of an observer. There's not a necessarily pragmatic attitude here. It's about what happened in the world. Systems actually have properties with respect to others when they interact, whether or not everybody is observing, which has the double advantage, as I said, of being non-instrumentalist, but not adding anything like extra variables, many copies of the observer or anything like that. Now, before giving just a bit of little additional details of how this works, why we don't think this way? Why people don't naturally think this way? Well, because I believe there's a culpable, and the culpable is this guy here, which you all know is Erwin Schrödinger. It's the bad guy of the story, which of course is not the bad guy of the story. It's one of the main fathers of quantum mechanics, and more than that, is one of the deepest thinkers of quantum mechanics. Is one of the person from which we have learned more about the conceptual aspect of the problem and this aspect of the problems. So I have an immense respect for Erwin Schrödinger and his writing, which are enormously enlightening. He's the one who understood entanglement, who understood so many things. But in his work in 26, which, let me just jump, which is after, this is the paper of Schrödinger, which is after all the setting up of quantum mechanics, after the calculation of the hydrogen atom. In his work in 26, he introduced the psi, this famous mysterious wave function, okay? which is not needed for quantum mechanics at all, which has some beautiful advantage. So with hindsight, he did two things. He did a technical step, which is translating this funny mathematics of non-commutative variables into an equivalent formulation, which is a differential equations, non-commutative variables, of course, are the operators that enter this differential equation. And this was very familiar to everybody. And this advantage, as he insisted, that it gives a visualizability, is visualizable, the wave function. And in fact, many of us learn quantum mechanics with psi. And we have, you know, the potential whales, and we draw the psi, and these are the orbitals of the electron in the atoms, the solution of Schrödinger equation, of the time-dependent Schrödinger equation for the hydrogen atoms. But careful, visualizability. It's great, it's very useful, but it can be very misleading, right? The heat, the caloric. I can take a picture of the caloric. There are cameras that take a picture of where the heat is. So I say, here it is. That's the heat. That's the proof that there is a caloric, a fluid, which is a heat. I see it. Even I can take a picture of it. So therefore, that's best ontology for thinking about the world. Or if I look at the motion of Mars and Venus in the sky, I mean, it's just obvious that there is an epicycle. It's so visible, so clear that is moving of an epicycle over a different, right? So it's easily visualizable. It does not mean that is the best way of thinking about the solar system. It's better to think that we're moving the Earth, and so on and so forth. So visualizability by itself, it's good as a tool, bad as an argument for taking a fundamental metaphysical position about the thing which you visualize. And Schrödinger himself, who, in my opinion, is a culpable of the misinterpretation of quantum mechanics in this sense, changed his mind entirely at the end of his life. And this is a quotation from him, in which he says there was a moment when the creators of wave mechanics, which means himself, of course, who else, nurtured the illusion of having eliminated the discontinuity in quantum theory, but the discontinuity eliminated in the equations of the theory reappear at the moment the theory is confronted with what we observe. And later on, even more strongly, he said, an electron, we should think it as an instantaneous event or a sequence of instantaneous event, discrete, connected by probabilities. So Schrödinger himself went away strongly from the idea that the best metaphysics for thinking, the best conceptual formulation of quantum mechanics is necessarily to take the wave function or the quantum state more in general as the thing about the quantum mechanics is talking about. So what is, so I think the one possible confusion theory from this perspective, I don't want to say that this is the only possible perspective, is that we learn the theory, quantum mechanics. What is quantum mechanics? Well, it's psi of x and t that satisfy this equation. Well, that's not true. If a teacher teaches quantum mechanics this way, he's cheating. Quantum mechanics about eigenvalues, about probability distributions. So there's another way of presenting quantum mechanics, which is just about this probability distribution and the spectra of the corresponding non-commutative observables, algebra elements, and so on and so forth. So whether you learn quantum mechanics as in the first box or in the second box, it's exactly the same theory. You're going to predict the same thing. You're going to describe the same thing that you do in a laboratory, but in the first case, your intuition is driven toward trying to make sense of this psi, and then you have the measurement problems, mysterious things. In the second case, you're not driven that way. You don't interpret psi ontologically, okay? I'll say in a moment how you interpret it, but you're a realist about values of variable that are realized in interaction. So what is psi? Well, you know, we know how to interpret a quantity in a new theory. Just look at the limit where we understand. We know what is mass in relativistic mechanics. Just take no relativistic limit and say, oh, that's mass. Of course, with some changes, but we recognize it. So what is the psi? Well, in the non-relativistic limit, it's just exponential of the Hamilton-Jacobi equation. And the Hamilton-Jacobi equation is something that nobody would dream of giving it a realist interpretation of quantum mechanics. It's a super useful tool, the Hamilton-Jacobi equation. The system that classical system we solve thanks to the Hamilton-Jacobi equation. But the Hamilton-Jacobi equation of a particle, it just described the variable that described the particle, not as something diffuse in space. So the Hamilton-Jacobi equation of electrodynamics, it describes electric fields and magnetic fields that take values, not a function on the space of all electric fields. So this is again various quotation of Schrödinger, in which basically saying the same thing, although I'm not going through it, including it's better to regard a particle not as a permanent entity, but as is instantaneous event. So this is again the previous slide. I think that this is a coherent way of thinking about quantum mechanics, in which you capture what I believe are the three physical aspects of quantum mechanics: discreteness, which is not there in classical mechanics. And I'm surprised how many interpretations of quantum mechanics don't talk about discreteness. What is H bar? H bar is the scale where you see the discrete of quantum mechanics. Photons are discrete, the electrons are discrete, the quanta of a field, the orbits of the atom are discrete. There's all this discreteness. This is core. Why? Because the key prediction of quantum mechanics, the values, which is the thing theory is talking about, are the spectrum of these operators, which are discrete. Probability, of course, and contextuality. Well, contextuality is due to the fact that these values are relative values. Just a slide to compare with three other very popular ways of looking at quantum mechanics. This, again, doesn't exhaust all popular ways of looking at quantum mechanics, which I put here just as an illustration, intuitive illustration of what is the relational quantum mechanics solutions of the Schrödinger cat paradox, right? In many worlds, what you think is that the state is real, and when you look at the cat, there are two you. In the reality, there is one you that sees the sleepy cat, and the other you that sees the awake cat. In the pilot wave theory, you have both of them in the wave function, but you have only one of them in the particle. I mean, the actual variables, because of course, pilot wave theory is not just about a particle. You can do Bohmian mechanics about any system, more or less artificially, but definitely you can do about any system if you want. The values which are specific. Take specific values, the guiding equation, and then there's the empty branches of the wave function. So one of the two wave function, it's empty. Branch of the wave function is empty. The other is full. In cubism, essentially, you don't think about the cat. You think about what you can say about the cat. So you can make all sorts of predictions, and the question what the cat really is, independently of your interaction with it, is just not posed. Relational quantum mechanics doesn't need empty branches, ontologically realized, doesn't need copies of yourself taken too seriously, allows you to talk about the cat, because I want to think that sometimes I'm the cat with respect to something else. So I want a picture of the world in which I'm one of the things of the universe. And the solution of the Schrödinger cat pseudo paradox is that with respect to me, the cat is neither alive, neither awake nor asleep. With respect to the cat, the poison is out or not, so definitely is one or the other of the two things, and there is no contradiction between the two, because we're talking about relational variables, not talking about absolute system independent values. So once again, from measurement to any interaction, from observer to any system, quantum mechanics describe how the system manifests themselves to other. Now, how am I doing this time? Just very rapidly, a little bit of more technicalities, because if you're confused about that, this is the key little technical aspect that makes everything works. The problem, if you want, is to to understand, that's one way of putting it, the conflict between the unitary evolution postulate and the projection postulate. And the answer of relational quantum mechanics, they're both right. They just refer to different systems. So if I have a probability, let's pair probabilities here, and PC comma A is a probability of C given A. If I have a complete set of alternative B, this equation must be true, right? The probability of C given A is the sum of a B, probability of C given B, probability B given A. But of course, this is exactly the equation that seems to fail in quantum mechanics when there is interference. If I think that B are properties of a system which are there independently of the observation A and C because of interference, right? The probability in quantum mechanics is square of amplitude, so you get the first terms plus the interference term. So if there is a system S3 interaction with system S1, S2, how is it possible that S1 has a property with respect to S2 and at the same time has no property with respect to S3? Well, it's possible because the interaction between S1 and S2 regards the value of S1 with respect to S2 has no bearing on a later interaction between S3 and S1 in the following sense, that the probability amplitude has a meaning. I mean, the module square of the transition has a meaning only when these two quantities refer to the same system, are variable with respect to the same system. While if it refers to the different system, have no meaning at all. So therefore, the probability of a value of C, okay, is not affected by the probability, but by the observation of the Wigner friend to the cat, right? So both can be right at the same time. So facts in this sense are relative to physical system, which is an expression which is used a lot recently in connection to all these so-called theorems and so-called experiments on the Wigner friends, which are all right, of course, and they're all interpretable in a way you want, with pilot wave, with Copenhagen, with many worlds. I'm not claiming that they distinguish between interaction. I'm claiming that they are naturally interpreted in relational quantum mechanics in this way. Now, one word about the coherence. The coherence plays no role in the interpretation itself, but it plays a huge role in answering a question, which is, if all variables are relative, why don't we see relative variables in everyday life? Well, the answer is because of the coherence, of course. When you have sufficient number of degrees of freedom, the labeling of facts becomes irrelevant. And this can be shown in a few lines. I'm not going through this few lines here. So if you take relational quantum mechanics and you apply it to a system where there are many degrees of freedom, and you don't look at this many degrees of freedom, you don't have a way to control many degrees of freedom, you immediately see that these probability amplitudes predicted by quantum theory don't need the labeling anymore. In other words, to see the labeling of the facts, which is what, according to quantum mechanics, is the relational quantum mechanics is the key discovery of quantum physics, you have to isolate a system. And that's why to measure quantum phenomena, you have explicitly, you have to isolate. So you see interference and so on and so forth. Good. So I want to try to finish early. So I want to close just with a couple of slides. The general idea here is that we shouldn't confuse relational with subjective. Okay. Subjective means that things are different depending on the subject. Subjectivity takes us towards instrumentalism or even toward idealism. I think the people who interpret quantum mechanics is only in the mind. I'm a bit horrified by that. The mind has nothing to do with what we're doing here. Relational means simply that there are some quantities which have values relative to something else. And this is a common confusion, right? When I say that velocity of the moon is relatively to the observer Earth or to observer sun, I don't mean that the Earth is it's a subject, or the sun is a subject. It's just a physical object. I mean that velocity, it's something that makes sense only when you have two systems, not when you have one system. And that's the core intuition of relational quantum mechanics. So quantum mechanics makes sense if you remember that, if you accept the idea that all variables are relational and they only take value in interaction relative to a system, and then everything is interpretable, it's fine, it's coherent, it's not instrumentalist, it doesn't need hidden variables or many copies of yourself, and so on and so forth. You gain that. The cost is that you have to digest the strong relationalism at the core of our description of the world. So the message here is not you have to buy this rather than something else. The message here is that this is an option. And I think it's good to realize that this option is available next to the options like pilot wave or many world or cubism or so on and so forth. So this is my last slide compared to the ones I put at the beginning. I don't want, I'll leave it there. I don't want to go into the specific list of advantages, cost of each. What I've insisted here is that one way of seeing the advantage of relational quantum mechanics is a way to avoiding the Schiller of strong instrumentalism of the kind of things cubism is being blamed by those who don't like it, and avoid the excessive baggage and postulation of things which might not be needed, like hidden variables, in principle hidden variables, or many copies of me in the many world, or unobserved fact in the more realistic versions of quantum mechanics. So I will stop here. I may actually leave. This is some of the key papers of relational quantum mechanics. I don't know if it is an update. I've taken this from previous. There are various. A lot of comments by philosophers on quantum mechanics. I want to point out the last of these. Carlo and Mariani on that discuss seriously the fact that some variables are not determined. So there's a strong indeterminacy. Not all properties, not all variables have value in relational quantum mechanics. Go back to this, and thank you very much. And I'm happy to take comments, discussion, everything.
Thank you. Thank you, Carlo, also for advertising the paper. So I have a lot of hands raised, as if you've completely forgot that you were supposed to write your name down, but that's all right. I can take note. So I have, the first one is from Jean, and then I have so many questions. Okay, I'm gonna try and write down the list. Meanwhile, Jean, you can start.
Okay, thank you, Carlo, for this nice talk, or at least I think I understood more or less, but I still have a problem of understanding really the ontology of your theory. And I put a link to everybody of a paper which discusses exactly this relational aspect of properties in the Breuil-Bohm theory, or in, they call it Bohmian mechanics. And you see, it's important to understand that I think most physicists are actually naive realists about operators. They think that when you measure something, you discover an intrinsic property of the particle. And that's impossible because of the no hidden variable theorem of Koch and Specker and Bell and others. And what you are saying is that, okay, everything is relational, but it's not clear how that works. In the Breuil-Bohm, it's very nice because you have the position of the particle.
Yeah, let's not talk about the Breuil-Bohm. Can I answer to this question?
Yeah, but can I finish? Okay, but let me finish. You can answer, but
we all know how it works with the Breuil-Bohm, so it's different here. So it's not relevant the way it works with the Breuil-Bohm.
Well, relevant or not, I don't know. But anyway, to me, it's relevant in the sense that that gives a clear picture of the world. When you say these are unobservable entities, well, the position is the only thing we ever observe. When you have a double slit experiment, you only observe the position of the particle. In fact, the thing which is unobservable is the wave function. That's constructed, but the position of everything is a position. So anyway, so let's go back to what happens at Breuil boom. The Breuil boom, all measurements are depending on the details of the measuring device. Spin does not exist, velocity does not exist. If you have a particle in a box which is at rest, if you measure the velocity, you get a non-zero answer. You don't discover the true velocity of the particle when you start the experiment. I mean, this is the beauty of Bohm's theory, is that it makes sense in a mathematically precise sense of Bohr's intuition, which you mentioned yourself, about the fact that you have to take into account the measuring device and the interaction between the measuring device and the particle. But of course, in your theory, it's not clear to me what the ontology is, and it's not clear at all to me, it's not clear to me what are the apparatus made of. Are they quantum? Are they classical? If they are quantum, how do we avoid things like Schrödinger cat and so on and so forth? I mean, I never got a clear picture of the world that is behind, in this relational quantum mechanics, even though I've listened to you before or read you before. And this talk was pretty clear, but I'm still baffled. And I think the way out, having position and nothing else as intrinsic properties of particle, is a way to think of relational quantum mechanics, but in a way which, to me at least, is clear.
Are you done? So the Breuil-Bohm theory, it's completely clear. It has no mysterious aspect, in my opinion. It's consistent, it's coherent. It assumes that there is some variables which are preferred. Of course, it's not just for a particle, but also in more complicated system. You have a set of a commuting subalgebra that to which you give an ontological meaning. You think that this is what they are, and that's one possible solution, one possible way of thinking about the theory, which, as I said at the beginning, it's coherent, it's good. There's nothing wrong with it. Like there are other coherent ways of looking about quantum mechanics. Relational quantum mechanics, it's a different solution, a different way, which is also coherent, which is based on the idea that it's not true that position is preferred. In fact, if you read the physicists or the mathematicians or the philosophers, each one think that there are some observable which are preferred with respect to the other one. If you read Alan Kohn, it says everything is momentum, because what we see is its colors and direction of light. We never see positions. We only see, that's another way of viewing it. If you use the Breuil-Bohm in electromagnetism, you have to struggle between electric and magnetic field, or to think directly of the photons. I mean, so this idea that there is one set of variables which is a priori preferred, I think is wrong. I think what is right is the idea that you can, if you want, choose a set of variables and formulate a theory in terms of that. Now, what happened, to go directly to your question, I understand that you are saying that you don't understand clearly what are the ontology here. I think if you read the paper carefully, you would understand. And the ontology here is that there are systems. So in like if you want to talk about particles, there are particles. You want to talk about fields, there are fields. Quantum theory is just depending on which quantum theory you're describing. A system is described by a set of variables. These variables are just the standard variables we use, so the functional phase space of the classical system. So for a particle is position, velocity, energy. They're related in the way they're related as functions on the phase space. These variables don't have a value at any moment. They take value in interactions because the physical interpretation is the way the system affects another system. So every time there is an interaction, a system is affected by some properties of the system, which are the ones which are realized in the interaction. And if you use that coherently, you can describe any measurement, any fact in the world, without assuming that these variables have a value even outside the interactions. If you want to make this assumption, then you're forced, because of the theorems you like, the theorems you were referring to, Cochran-Spencer, etc., you're forced to reduce your variables that always have a value to an abelian subalgebra. But you can have Lx, Ly, you cannot have Lx, Ly, Lz always having a variable, Lx, Ly, Lz being the different component of the angular momentum, but you can have them, each one having a variable when the particle interact with a Stern-Gerlach apparatus oriented in that particular direction. So if you don't pretend all variables having a value at any time, you're not constrained by the theorems like the Cochran-Spencer. And the point is, let's separate two things. We always confuse these 2 points. One thing is the coherent of an interpretation. Relational quantum mechanics is coherent. Pilot wave theory is coherent, both in Anthony version and in the probability, fixed probability solution version. They're both coherent. So one thing is coherent. One thing is that, well, I don't like the idea of breaking Lorentz invariance with the bomb. Therefore, I find this incoherent. No, it's not incoherent. It's just you have a metaphysical prejudice which may be correct for or against some. So let's distinguish. I don't understand something from it seems to me that it is incoherent.
Okay, so I want to ask to Alexei. I saw your end, but then you didn't write your name down.
Go ahead, Cristian. Thank you. There are lots of other questions. Mine is not urgent.
That's all right. Okay, so the next one is Anthony.
Hello.
Anthony.
Carlo. Well, I would have some historical comments, but let me just go straight to the meat of it. Okay, so relative facts. Now, from what I understand, the recent work that you've been doing about stable fact, this idea of stable facts. So presumably, I mean, it looks as if it's some sort of approximation, right? There's some order epsilon terms. So I mean, in principle, something, I mean, let's say there was some super advanced extraterrestrial being with a technology far beyond ours. In principle, they might be able to do an interference experiment with the Earth. And in one version of the Earth, we're having this conversation. In another version, I didn't manage to get up this morning. I'm still in bed. We didn't have this conversation, okay? And then relative to that super observer, it would not be correct to say that we had this conversation. Is that accurate?
Completely.
Right, okay. So now, so as I said here, I mean, this is the issue that I have a problem as to whether this is realism, okay? I mean, look, I'm happy to have relative facts like, the velocity, my velocity is relative to the kitchen or relative to the Earth or whatever. I mean, there are some facts that well, I mean, I think there's some facts that people generally agree are not relative, like, so the velocity of the moon is relative, but the fact that the moon is not made of cheese, it's not relative, it's just a fact, okay? Not for me, the fact that we're having this conversation, it's the extreme, I mean, admittedly, this is a bit of an extreme example, but in principle, the fact that we're having this conversation is a fact relative to us. Relative to this super observer, it might not be a fact. Now, if that's a consequence of relational quantum mechanics, my feeling is that, hang on a second, look, if this super observer comes to the conclusion that we never had this conversation, then I would say he's just wrong. Because we're having this conversation, it's a fact. relational quantum mechanics seems to say, well, no, you can't say that he's wrong. That you know, we're having this conversation. There's a fact relative to us, relative to him is not a fact. I can't. It doesn't make sense to me as realism.
Yeah. So I agree 100% with everything you say. I think it's all correct. I have two answers. One is that the realism, it's a matter of degrees in a sense. So you can define realism in a number of different ways. From a very weak way, saying I have a realist picture of the world where it's nothing to do with my mind, with subjectivity, with observations, with instrumentalism, with just a description of how the world works. Or you can have a stronger definition of realism. Let me give you one that perhaps you might agree upon, which might be closer to what you have in mind, which is that the world can be described as a set of systems, each one having a properties by themselves, not with respect to something else. I suspect Einstein would be happier with this version. So in this stronger sense, the relational quantum mechanics is not realist. I agree. It's a weakening of realism in some sort. So you may your reaction is, well, I'm not happy because sort of metaphysically disturbs me. I respect it entirely. It's the same kind of reaction that many people have, lovers of one way of viewing quantum mechanics, just find that there's a metaphysical challenge to some of their metaphysical prejudices, and this, you know, you can make all sort of. So
Carlo, can I follow up? Just ask you. I mean,
sure.
how do you feel?
Anthony,
about...
can you make it quick if you can?
Yes, yeah. Yes, Carlo. How do you feel about the fact that maybe with respect to some super intelligent observer, this conversation never happened?
Okay, yeah, I think that when I say with respect to some superintelligence, what happened, I'm only talking about interactions because you and I conversing and this observer, the superintelligent observer. So I'm not talking about, when I say with respect to system A, I'm not talking in some idealistic metaphysical sense. I'm talking that to talk about properties of you and I with respect to that system means talking about interaction between you and I in that
understand, system. But you know, maybe next year this super observer does an interference experiment with the Earth and draws this conclusion that this conversation never happened.
Oh, no, he doesn't draw this conclusion. Sorry, I perhaps it was not clear in there. He draws the conclusion that in the values describing you and I with respect to him have no value at this time t, because if you make them having a value, he he would get the wrong. He wouldn't get interference.
Sorry.
I understand, but presumably you're not saying that, well, look, we had this conversation, he just doesn't know about it. Presumably
no, I'm not saying that.
For him, it never happened. There's no, you know, there is no conversation.
We agree on the substance. We only disagree on the, oh, come
whether
on.
It's plausible. No, fair enough. Fair enough.
Yeah.
Okay.
Okay, so next one is Eric Curiel.
So, Carlo, the following is not meant to be. Hi. The following is not meant to be a challenge because I actually am, by and large, extremely sympathetic to what you're saying. I really just am trying to understand some details. So, generally speaking, when you have two systems, they tend to interact at the same time in more than one way. So, if you have two charged particles in relative motion, they interact both gravitationally and electromagnetically. But those interactions are mediated by very different physical quantities. The gravitation is mediated by position, distance. The electromagnetism, at least in part, is mediated by velocity, from Lorentz-Force law. And so, if you have two simultaneous interactions, that are mediated by different quantities, and those two quantities are, according to quantum mechanics, incompatible. How do you describe that in this relational framework?
Yeah, very good. This is this goes into technicalities. It's a very good question. I've been thinking about that. You have let me just sketch the answer. You write, you're a physicist. I write the Hamiltonian. I write the physics of this in the Hamiltonian language. So I have the Hamiltonian 1 plus the Hamiltonian of the 2 plus an interaction Hamiltonian, which might have many terms. But the interaction Hamiltonian is a number on the phase space of one and the other. Okay, so given the configuration of one, it's just a function on the phase space of the other. Given a configuration of S2, it's a function on the phase space of S1. That's the function which is being measured, so to say. I mean, it's a little bit technically more tricky, but that's the point. So it's not two different interactions. It's an interaction which is a sum of two things, which might depend on a combination of position and velocity in some manner.
Okay, I have to think about that. Thank you.
Yeah.
Next one is Davide Romano. We can't hear you. Okay, I go to Aurelian, and then if Davide.
Oh, sorry. Yeah.
Yeah, you can go.
So yes, thank you, Carlo, for this great talk. I have
Thank
just
you.
one small technical question and philosophical one. The technical is classical limit of quantum mechanics. You take the wave function to be the phase of the Hamilton function. Yeah, that's one way to see it. If we take the Jacobi approximation, but if we are in a decoherence regime, then in the classical limit, the wave function seems to be more something like a Gaussian packet. At least this is what works by Zurek and other indicate that, pointer state or something like Gaussian, that these are then pointing phase space. So I want to say what you want to say about that. The other question is just philosophical. I was curious to ask you about the role of the collapse. I mean, it seems that, okay, we change observer with interaction, fine, but do you still need the collapse of the wave function? And if so, do you think it's a problem? There is a huge philosophical literature about that. So.
Yeah, so it's two different questions. The first question is you're saying, well, there are two different semi-classical approximations here. There is a semi-classical approximation which says that in a sufficiently semi-classical situation, the wave function is approximated by the Hamilton-Jacobi classical function, and the other is that well, wait a minute, the approximation is given by wave packets. Yeah, that's correct. What you say is correct. It's just two different kind of approximations. One is a wave function that can track a classical evolution up to quantum phenomena. They're not in contradiction with respect to one another, because the second approximation, it's one way of realizing the first by giving a sufficient amplitude. In both cases, the phase obeys the Hamilton-Jacobi equation. So it's just language. My argument about the approximation with the Hamilton-Jacobi was just a way of arguing that if you don't give a strong ontological weight to the wave function, you're not doing something strange. That's the only point. I mean, it's not that I actually use this relation with the Hamilton-Jacobi in any concrete way in the relation interpretation. Second question is about collapse. Good. So from the relational perspective, what is collapse? Well, of course, suppose you learned quantum mechanics in a relational way. Then you only talk about interaction between systems, nothing prevents you to use wave functions. In fact, nothing prevents you to use states. In fact, you want to use states. States are always relative states. When there is an interaction, you want to keep track of the previous interactions to have probabilistic predictions about future interactions, right? This is exactly what happened in the lab. So how do you keep track of past interactions? Well, you can in the math, and you call this the state, the quantum state. So the quantum state is the way you keep track of previous interaction to make probabilistic prediction about the future ones. Okay. Therefore, you use the quantum state epistemically. All states are relative states in the sense of Everett, and they express the state of the particle at some time, express just the information you have about previous interaction, which allow you to make predictions of next interaction. Obviously, when a new interaction happens, you have new information, so you have to change the state. That's a collapse postulate. Mm-hmm. Since the interaction between system A and B doesn't affect anything for system C, if system C has some previous information, he keeps using unitary evolution, because that's what that's how the time dependence of the prediction depend. So the collapse postulate come in the same way in which comes in all the epistemic interpretation of quantum mechanics, like Beats or else, without being a physical process, like in the physical collapse, just perspectival process in a sense.
I see the point. Okay, thank you very much. Thanks.
Okay, I still have 7 or 8 questions, so I would ask everyone.
I'll try to be short in the answer.
Yeah, everyone, you and also who asked questions. So I would like to hear from everyone in the list. Next one is Aurelian.
So I will try to be very short. So thank you very much for this this good talk. It's very interesting. I have one historical comment, but it's very related to what says Anthony Valentini before. The first one is, my first comment is that the action in Hamilton-Jacobi equation is maybe in the classical physics only an abstract concept, which is not necessary, which is completely eliminated when you are going to, let's say, Newtonian equation, but you cannot do it in quantum mechanics because you have the quantum potential, and then you get what is nowadays called as Bohmian mechanic. This was only a historical comment, but my general comment is kind of question is really related to the point of Anthony, is if Alice is observing Bob and Bob is observing Alice, and everyone is telling that he's the center of the universe, then I will say that they are both right, and then Bohmian mechanic again is the only ontology which is working for putting all the things in a consistent way. But of course, I agree that your perspective is good, but it's a kind of club of solipsists, I would say. But there is no common agreement possibility between these guys.
Okay, so good. So the 3 points I try to be very first. The first one, I disagree completely. Okay. You said that we can do without Hamilton-Jacobi, but we cannot do without wave function. I disagree completely, and I gave the proof. I mean, there's no wave function in the Bohr-Jordan formulation of quantum mechanics. I mean, you can give a formulation of quantum mechanics and never mention a quantum state, just mentioning variables that take value at some precise moment of time and probabilities between them. So no, I mean, of course, if you say, I want to use Bohm theory, therefore I want to use a quantum potential, therefore I want to use, then of course you have to use a wave function, but because of the choice you've made in the formulas, not because of the theory itself. Let me jump to the last point, which is solipsism. There's a lot of blah, blah, blah about solipsism in Facebook right now. I find it completely non-understandable. We see the same world. Obviously, we see the same world. And, you know, the coherence shows why. Relational quantum mechanics is about relations, how systems interact with one another. So it's not about, it's nothing solipsist. It's the other way around. It's the less solipsist thing you can imagine. Plus, if you use quantum mechanics, just the standard formulas of quantum mechanics, it's a fact that if I interact with an atom, okay, and C spin up, and Anthony Valentini interact with the atom and interact with me and measure the spin in the atom and ask me what I've seen, it's from the tensorial structure of quantum mechanics immediately implied that he finds consistency. Namely, if he sees spin up, I'm going to tell him spin up. If I see spin down, I'm going to tell him spin down. So it's not true that different observers give different totally unrelated picture. They're enormously related. What's happening is that there's an H-bar discrepancy in the fine details because the perspectives, if you want, don't fully match all the way down to the details, unless, of course, there is a decoherence where they match all the way down entirely. So this is as far as solipsism as you can imagine. It's all about, the theory describes exactly how different observers communicate to one another. And the recent beautiful theorem experiments by, Renner and company, Bruckner and so on, make clear where, if you go very, very fine, you see the subtle discrepancies in the non-matching of what we would call the perspective. But that's not solipsism. This is just like, when we look at a chair from two different positions, you look something else.
Thank you. Okay. There are so many people I cannot continue to discuss, but it's very interesting.
Lev, you can go.
Thank you, Carl. Maybe a comment. As I can see, before Schrödinger, there was no quantum theory. There was no kind of real ontology. There are all kind of variables, and I understand your approach also has this property. Some variables are defined, some variables are not defined. And came Schrödinger and said there is ontology, there is a quantum state. But let's not go to this philosophy. I want kind of maybe more technical question. You repeat many times that the coherence helps you in some or other way. Assume there is a super intelligence, super technology, Ken Wigner, and does the only one thing. All macroscopic objects which are kind of interact with environment, he eliminates entanglement with the environment. He eliminates the coherence. How it will help him, how it will change anything? I don't believe it will change anything. And you say that then your theory cannot be defined, or we will not see things. Well, what is the role of the coherence? I don't understand.
Yeah, thank you. So with respect to the second question, the role of the coherence in the definition of the theory is zero, nothing at all. So the coherence is not needed for this particular interpretation of quantum mechanics. You can ask questions like why, when there is some macroscopic things happen, I don't see certain interferences. Well, because of the coherence, which is the standard use we have of the coherence. So the coherence explains certain facts that happens in our macroscopic world, including the enormous stability of our macroscopic world. We all agree enormously in detail of the world. Regarding your first question, I agree with you. If you, as I know you do, are deeply convinced that the ontology of quantum mechanics is a wave function, then of course for you, quantum mechanics is born with Schrödinger. But you're putting the charts in front of the horses. If somebody is not convinced that the ontology of quantum mechanics is a wave function, then quantum mechanics existed before Schrödinger. And I find this a more convincing option because I can use matrix mechanics in the way it was in the mind of Born and his collaborators and do exactly all the prediction, exactly all the laboratory experiment, exactly everything without ever using the Schrödinger equation, a psi or anything like
that. Renato, sorry, Lev, I'm so sorry. Renato, you're next.
So thanks, Carlo, for the nice talk. I have a question that relates to something I think we discussed a long time ago when we once met in Italy, I think, which is about where this relative view kind of stops, because you always have this analogy. For example, the one you brought about the moon has a velocity relative to Earth. And then, of course, if I take this analogy further, I would say, now, this property itself, that the moon has a velocity relative to Earth, is itself again a property of the common system moon-Earth, so to speak. And now in relativity, I would say, okay, that's no problem. I can now use that as a fact from the outside. I can come and say, if I now, for example, know the Earth's velocity, I can calculate the velocity of the moon relative to this, or if I know Earth's velocity relative to sun, I can combine things. Now, as far as I understand, we cannot in general do that. And you mentioned just before the thought experiments we have where somehow observers try to combine knowledge. So my question is, somehow, where do you do, or what's really the, let's say, guideline of when can we somehow combine relative facts? I mean, in relativity theory, it's very clear, we just add velocities, but here we know from these thought experiments that, for example, if you have measured the spin and it's up, and now I somehow know you have measured up, but I haven't seen the spin, then it is very particular scenarios that we construct. It's not clear I can now conclude from the knowledge that I know you measured up, that the spin is indeed up. So is there some way you see around this, or let's say a rule set, or would you just say, no, in general, we cannot combine these things?
I would say all the way through, you cannot combine these things. So facts are relative, as you would put it. They cannot be combined. Or they can be combined in an extraordinary artificial way, sort of violating all sorts of other things that we expect not to be violated. But then it's not an attractive alternative either. So I would say in that sense, it's relational all the way through.
Okay,
I understand what you say, and
yes,
perhaps,
no, I mean,
perhaps not everybody's following our conversation, but I think I would agree with its complete. Of course, concretely in our everyday life, because of the coherence, that's what we all agree. Facts are facts, but facts are facts. Period. Just because, thanks to the coherence, we fail to see that they aren't really so when you go down to the details.
Alissa?
Yeah, I'm afraid I had the same kind of question as Anthony about the Wigner's friend. Your response to that's not completely satisfying. I wasn't going to push it as a thing about like you not being a realist enough. It's just, so I don't really think, I don't think this is a metaphysical prejudice. It's like just basic epistemology. I mean, that's the way Wigner pushes it in his paper on mind-body problem is like, I know, like in your pictures, you had the little cat, and relative to the cat's, you know, there's a cat that's alive. Relative to the person, it's just all gray. I know it's not gray. Like that's just, I mean, if I know anything, I know there's something going on here in my mind. So it seems like from this other perspective, you know, that Anthony was talking about, that perspective is wrong. And that just seems like it's not a prejudice. It's like, if we know anything, we know there's something going on with us. So I guess, I don't know if there's more to say there. I'm
not sure I follow. I'm not sure I understand the question. It seems to me you're saying,
I'm just trying to push like Wigner's point against a Copenhagen interpretation, you know, that is equally seems to apply to your view. In your view, there's no objective fact about whether or not I'm, you know, conscious, right? And, or, you know, in his example, whether we're having this conversation. And it seems like, you know, it just seems like, you know, the starting point of all of our epistemologies is that we know we're having certain experiences, or we know, you know, maybe that's too theoretical a way to put it, but we, this is happening.
Okay, so let me try to,
somehow.
Yeah, let me try to answer. So,
it's not a relative fact.
Well, let me try to answer. I think that everything which has to do with our being aware or conscious, everything, it is a fact of nature relatively to us. Okay, not because we are specially, not because of any idealism of any role of consciousness by itself or mentality itself, like Wigner or somebody wanted Wigner to say. It's just in the same sense in which the sky rotates relative to me, and I observe a rotating sky, but the sky doesn't rotate. It's just a property of the sky in relation to me as a physical object, not as a consciousness observer. There's a true property of the sky relative to me, and that's a fact. But the point is that our experience is not the experience of the super observer outside that many of you have in mind. That's the point. Our experiences are embedded. We have a perspectival view of the world because we're inside it. And us being inside it, quantum mechanics tell us about perspectival view from the inside. I think quantum mechanics also tell us the perspective of somebody outside who is not interacting with anything, but with respect to that person not interacting with everything, well, I mean, there's just, maybe a wave function if it has interacted in the past, which is just he's remembering whatever has interacted in the past and nothing happening. But that's not the point. The point is that quantum mechanics is not about the description of something with which I'm not interacting. It's a description of something with which I am interacting. So it's the other way around. I think that precisely, Wigner's story tell us that a good way of making sense of quantum mechanics is not thinking from the outside, it's thinking from the inside. And thinking from the inside, it's coherent with our experience, it's coherent with mathematically. We have to renounce a certain form of realism very strong, which is the idea that in some sense all perspectives agree on some common set of values, and there aren't. That's, I think, what one way of looking at quantum mechanics. I insist, there are other ways of looking at quantum mechanics, just reduce to a subalgebra which is commute, which is pilot wave, or just try to derive everything from the wave function in some complicated way with many walls and so on and so forth.
Okay, we are very much running late. I would like to take at least a 5-minute break before we start the roundtable. And I mean, I guess we can have at least some of the questions during the roundtable. I still have 4 names, which I'm going to remind later, which are James, Hippolyte, Alexei, and Guido, who had a question. And I'm sorry, you can ask this question at the roundtable. Sorry, we didn't have time. Okay, now let's have a 5 minutes break, and thank you, Carlo, a lot.
Thank you.